And so Wageningen tries to address these. And for all of these, I hope you can imagine and you're aware that soil information is like really important in order to tackle these challenges. For example, food security, well, that's related to agriculture, agronomy, and well, you're students of an agricultural university, so you know very well that the conditions of the soil also are really informative in terms of what you can grow, what the yield can be, etc. So soil information is key, and that is why maybe I work on digital soil mapping. Well, Wageningen University is actually a top university in the world in the domain of agricultural sciences. We are actually ranked, in last year in the #1 university in the domain of agricultural sciences. So although we're not like really big, we are, I think, a top university. Now, I work with the Wageningen University, but I also work for ISRIC World Soil Information. This is an institute also based on the Wageningen campus, but it's not part of the university. It's a separate institute, but we have like an affiliation, a cooperation agreement with the university. And it was founded in 1966 upon recommendation of the FAO, UNESCO, and the International Union of Soil Sciences. It's funded by the Dutch government, and well, we have also we are the World Data Center for Soils. So it has a mission as well, and the mission is to produce and serve quality assessed soil information, and we do that freely. Okay, so I'll show you a few products later on, and all the soil information that we produce, we share it with the world for free. For example, with you. So if you want to make use of soil information and you need it, maybe for India or for some other part of the world, then you can check what does ISRIC have to offer, because we have soil data. We don't collect it ourselves. We assemble it, we merge it, we harmonize it, and then we make it available through web services. And we want to also stimulate the use of this information through capacity building. Maybe my lecture today is an example of that: awareness raising and direct cooperation with users and clients. One of the products that ISRIC produces is the World Soil Information Service, WOSIS, we call it. And here you see that for over 190,000 locations on the globe, we have soil information stored in our database. It's freely available. You can simply Google WOSIS and you will find the right spot. And then you can download these data. Well, like I said, you are somewhere from over here. So probably, well, we don't have that many data, not a high data sampling density from India. And of course, we know that in India, there is much, much more soil information. Actually, we also work with institutes in India to get the soil information system of India to help develop that. But some parts of the world, we have a high density. Also Russia, we don't have much data, but for example, Europe and the US, and parts of Australia and Brazil, we have a high sampling density. But all of this is available for anyone who would like to use it. We use those data, and that's actually the topic of today's lecture, also to do digital soil mapping. And at ISRIC, when we do digital soil mapping for the whole globe, then we produce a product which we call SoilGrids. You may also go to this website and you get all the information about SoilGrids, but I'll explain it a little bit also in the lecture today. And you can download maps of soil properties. So this is just one example. This is I don't know if you can read this, is maybe a little bit small font size, the soil organic carbon stock everywhere in the world. But we also have maps of soil texture, cation exchange capacity, pH, all the basic soil properties. Okay, and that SoilGrids map, and now we're actually going to really start with our lecture, SoilGrids was produced using digital soil mapping. So what is actually digital soil mapping? Okay, so just remember, whenever you have a question or a comment, feel free to put it in the chat box. So this is the definition of digital soil mapping. It's the computer-assisted production of digital maps of soil type and soil properties. I gave you a few examples of soil properties just a minute ago, using mathematical and statistical models. So we make use of statistics. And what do these statistical models, mathematical and statistical models do? Well, they combine information from soil observations. We cannot make soil maps without soil data, obviously. So for example, we need the WOSIS soil profile information to construct, to create those digital soil maps. But that's not the only source of information we use. We also make use of information contained in, explanatory environmental variables. And this is where the remote sensing comes into play. Because soil is not isolated from its environment. Soil is is influenced by what we call the soil forming factors. Climate, organisms, usually these are like plants, trees, but actually they also include animals and even people, you might say, because people, of course, have a strong influence on the soil. Climate, organisms, parent material, the geology, you might say, and topography, the terrain, is the slope, the aspect, all these kind of terrain properties are influence the soil. And maybe the soil also influences the others, but in digital soil mapping, we really benefit from the fact that the soil is not isolated from the environment, but is influenced by these environmental conditions. So the famous Russian soil scientist Dokuchaev, he came up with this, let's say, conceptual model which says soil is a function of climate, organisms, relief. Relief stands for topography over here, and parent material, P, and time. Of course, time also plays a role. And we call that chlorped. So this is the soil forming function model. And we benefit from that in digital soil mapping because, well, how does it work? Well, let's have a look at this scheme. Maybe this scheme will appeal to you because it is like a flow chart that tells you how does the digital soil mapping work. We start from the top. And well, we need soil data, like I said. So soil profiles where we measured the soil. So we have soil measurements at locations. And we standardize them and we merge them and we bring them together in the soil database. So at all these black dots, these sampling locations, we have measurements of the soil type and the soil properties. But we also need those environmental variables. So through remote sensing, like I said, this is where remote sensing comes in. We have lots of maps. Maybe Landsat, MODIS. Well, I'm not a remote sensing expert, to be honest. So there's so many satellites up in the sky, and they all measure the globe, and they measure information about climate, like, for example, temperature, precipitation. They measure vegetation density. Well, they measure elevation, and from a digital elevation model, we can compute all those derived geomorphological properties like slope and aspect and topographic wetness index and catchment area and upstream area. I'm not sure what is your background, but I hope it all is not complete new to you, that you have an idea. And maybe we can even also collect from the sky through satellites information about the parent material. So we use remote sensing to collect those environmental variables, and we call them covariates often in digital soil mapping. And maybe, well, it's a common term, so maybe you're familiar with that. Covariates, and we have lots of them, right? So we have maybe 50 or even 100 or 200 of those covariates, and they are available as maps. And that's important to recognize. The soil data are only point locations, but the environmental covariates, they are actually already maps, usually raster maps at a, well, some kind of certain resolution. It could be any kind of spatial resolution. The finer, the better, maybe, because then we can really make fine scale maps which have a lot of spatial detail. Okay, then the next step in digital soil mapping is that we do a GIS overlay. So basically, these point locations are overlaid on top of all these covariates, and in that way we construct what we call a regression matrix. And a regression matrix is simply has as many rows as there are locations and has as many columns as there are covariates plus the soil. Because the Y over here is the soil property of interest, for example, the clay content of the soil, and X1, X2 up to XP, these are all those covariates. So basically we construct a matrix that has the paired observations of the dependent variable, the variable that we want to know, the soil property, and all the explanatory variables, the covariates. And this is the kind of information we need in statistics to fit a model that predicts the dependent variable from the independent explanatory variables, like in regression, and I'll give an example of that in a minute. But we also make use of machine learning a lot. So I'll talk a little bit about that as well. For example, random forests, gradient boosting, neural networks, deep learning, support vector machines. You know, I'm not sure how familiar you are with all these techniques, but nowadays we have a really, how to say, a large library of functions that we can use to train to fit a model that predicts the dependent variable, what we want to know, from what we have from the explanatory variables. Because remember, our goal is to produce a map of the soil property. We know the soil at point locations, but we don't know it in between those point locations. But if we can establish a relationship between the soil and the explanatory variables, that we can apply that relationship to predict the soil also at locations where in between measurement locations, because we have those explanatory variables, we know them everywhere. We have them available as maps. Okay, and that's really, you fit your model, you have your model parameters, and you apply your model to predict, and that's how you get your map of your soil property. So this is basically, you might say, the end product of your digital soil mapping. Now, what we also often want to do, and I'll talk about that a little bit more as well, is we want to be able to quantify, to characterize how accurate is that map? What's the uncertainty associated with that map? It's only a map, it's only a prediction. It's not the true soil property. So that's where we can use cross-validation or independent validation to compare the predictions with independent observations. So this is where you go a little bit back, you might say, to the original data to see how well did I actually do. Okay, so this is in a nutshell how digital soil mapping works. I hope it was more or less clear the way I explained it. And well, let's just continue and go a little bit into the detail of some of those aspects. And I'll also give you plenty of examples in the coming slides. And as before, whenever you want to ask a question or have a comment, feel free to submit it. I can see you, by the way, now. I can see you sitting and I can see people, I don't know, are you watching your mobile phones? That's not, you're supposed to pay attention, right? Okay, good. Let me continue. Yeah, so these covariates, they are really crucially important. And you know, that's why digital soil map actually is like booming. You know, 25 years ago, we didn't really have it. And now and we only had like conventional soil mapping. I'm not going to talk about that. Conventional soil mapping has a really great value too. It's not that we are in competition and that me as a digital soil mapper would say that conventional soil mapping is no use, and no, the opposite. But digital soil mapping has really rapidly increased because, well, for one thing, we have much more covariates available and much better covariates. So these are two digital elevation models of the same area. And this is maybe what we used to have. It's pretty coarse, not very detailed. And nowadays we have so much better, more high resolution, detailed information. And you can imagine, for example, you see here a riverbed, right? Well, if you look very carefully, maybe you can see it here as well, but it's not nearly as clear as it is here. So you can imagine that such a highly detailed information is much more informative also about the soil than such a coarse resolution map. So because we have so much more covariates available nowadays, digital soil mapping really could take off. Here are, well, this is a pretty old slide, and I'm not sure it's very impressive to you, but just to give you an idea. So from this digital elevation model, we can derive all these derived terrain properties. I think I mentioned already slope and aspect, compound topographic index, the curvature. So all these geomorphological attributes can be derived from a single digital elevation model map. And all of them could have a relationship with the soil. And we benefit from that in digital soil mapping and satellite images. So we have so many of them. And you are doing a course on remote sensing. So in the previous lectures or in the next lectures, you will get much more information about that. So there's so many, such a rich data source satellite images, and we can benefit from them in digital soil mapping. And that is what we do. But it's not only satellites that provide us with information. We can also use airborne information. So maybe we can, for example, use a gamma ray spectrometry. Maybe, I'm not sure if satellites can do that too, but here's an example where it's done with an airplane. And you get maybe images like this, and they maybe are a useful source of information about the parent material, the geology, because they can, detect radioactive elements in rocks and soils, and they tell us something about the composition of the rocks. What material is it made of? And that, of course, tells us also something about the soil. And now, yeah, let's go even lower and let's go to drones, who nowadays, of course, or maybe not on a global scale or on a continental or a country scale, but a regional scale, maybe catchment scale. Drones could be very useful source of information. So we can measure lots of things through the drones, also using sledges behind a tractor or device, and maybe there's a GPS, of course, because we also want to record where are we uh, collecting the information. And for example, electromagnetic sensors measure all kinds of things about the soil, and somehow they can be informative about the soil property that we actually want to know. So digital soil mapping is really about predicting the soil from the environmental variables, from the covariates. So here is a little bit of mathematics, but not very much. So basically our model says the soil at any location S in my study area is some kind of a function. Okay, I see. I read here now that two participants raised hands. I'm not sure if that was on purpose. I cannot see who did that. Oh, no, three even. So if you have a question, put it in the chat, okay? Because then I will be able to see what the question is about. In the meantime, I'll just continue. So the soil at any location S is a function of the covariates. That's the core of digital soil mapping. But no matter how hard we try, how strong the relationship between those covariates and the soil property, the map will never be perfect. The relationship will never be perfect. So we also have a stochastic residual part, the unexplanatory part, the noise part, the unexplained variance, the residual. Maybe you're familiar with that kind of terminology. So we have an explanatory part, a function that relates the covariates to the soil property, and then we have a remainder, a residual. Now, what is interesting is that, of course, that residual is also a function of the location. So at every location in our study area, that epsilon exists and has a value, and we know it at the measurement locations. And that's where we can use geostatistics because it may well be that this residual is spatially correlated. I'm not going to address geostatistics today, but the next slide is a little bit about that, just to give you a little bit of a hint, because it's often used in digital soil mapping, making use of the fact that observations are spatially correlated. But we also have the relationship with the covariates. And here is an example of that, a simple example. The soil depth. So basically, whenever we go in, for example, in your region, if you go any location, maybe you go outside and go to a nature area and then you start drilling, augering. At some point, you hit the bedrock, the rock, the hard rock. So where does that happen? At 20 centimeter depth, at 50 centimeter depth? You know, that's the soil depth. So how deep is the soil? How deep is the hard rock, the bedrock? Well, that varies in space. One location, the soil can be thicker than at another location. So there may be, and maybe that soil depth is related to explanatory variables. For example, it may be related to elevation. I can imagine that down the valley of a catchment, the soils are thicker than high on the plateau, high on the mountain, right? So I think there is some kind of a relationship between soil depth and elevation. And I express this here by including elevation as an explanatory variable to help predict the soil depth. And here I've used a linear regression, okay? A multiple linear regression. I hope you're familiar with it. And the betas here, they are regression coefficients. And okay, let me ask, this regression coefficient beta 1, what do you think? Is it positive or negative? So yeah, I just read a note from Shabir that you can put your answers or questions in the chat box. So I hope at least one of you will provide me with an answer to my question, this beta 1 regression coefficient. What do you think? Is it positive or negative? Okay, Richmond says positive. And Danny as well, and Fauzan says also positive. Both, Bilal. I don't know what you mean by both. You know, this beta 1 cannot be at the same time positive and negative. Most of you say positive. So if it would be positive, it would mean that the bigger the elevation, the bigger the soil depth, right? Because you multiply with a positive coefficient. So the higher I am higher in the mountain, the thicker the soil. And if I go down to the valley, the soil becomes thinner. Is that true? Yes, exactly. It's negative. I think beta 1 is negative because the higher the elevation, the thinner the soil, the smaller the soil depth. What about slope angle? You know, steep soils, steep terrain, you have thin soils because you have a lot of erosion. Akarai, again, you're right. Yeah. If you have a flat surface, there's no erosion, the soil can grow thicker. So I think beta 2 is also negative. What about beta 3? Is that positive? That's the last one I'm going to ask. Positive or negative? I'm not sure what you're responding to. Yeah, okay. Yeah, I think positive, Akarai. Yeah, you know, the higher the vegetation density, so a lot of vegetation, then, well, first of all, when you have erosion, then it gets trapped, right? You get more, like you have more sedimentation rather than erosion. So when you have a high plant density, I would expect that you have a thicker soil because the soil material accumulates. And also the roots of the plants, you know, they break down the rocks, you might say, and they create soil. So if you have a bare soil, for sure you have a smaller soil depth, not such a thick soil. Maybe your bare soil actually has thickness 0. So, I expect a positive relationship between vegetation density and soil depth. I think it's important we pay some attention to this because, whenever we fit a statistical or mathematical model, we also like to be able to interpret it and to say, does it actually make sense? So it's good to have a hypothesis of what these beta regression coefficients will look like. And then when you fit your model based on the data that you have, well, we don't have a computer practical today because otherwise I would have let you actually do that with a real world data set. Then you find, okay, what is then the fitted value for beta 1? And is it indeed negative as I expected? Yes or no? It's very important that you're able to interpret models and to check whether it makes sense. Now, we do our best to fit this trend, but the trend is not equal to the true value variable. There is always a residual because no matter how hard we try, we can never get a perfect model. So we have to pay a little bit of attention to this residual. But before I do that, let me look at the question of Fauzan. In case of peat soil, organic soil, which parameters should be paid attention in predicting soil depth? Yeah, that's a very good one, Fauzan. A peat soil, I don't, well, soil depth can sometimes be, well, tens or maybe even 100 meter thick, right? A soil. So a peat soil, I don't know, you have your peat layer, but below the peat, there is a mineral soil again. And at some point, you will reach the hard rock. But maybe that is at a 15-meter depth or 25-meter depth. Or actually, the country where I live, Netherlands, we are we are not in erosion. We are in the delta. We live in a delta, and so we have a sediment type of country, and so we have building up a lot of soil material. So for us to reach the bedrock, when we do soil augering, we never reach the bedrock. Maybe a few parts of our country, but most of our country, the bedrock, the soil depth is tens or 20 or 50-meter deep. So, and I think for peat soils, eventually, of course, you reach the bedrock. But soil scientists are usually only interested in the top 1 meter 20, the top 2 meter of the surface of the earth. So we don't really go any deeper than that. And then we would simply say soil depth is bigger than 2 meter. And we don't really care whether it's 5 meter or 15. So that might also be the case for peat soils. I hope I answered your question. Okay, and Bilal did some extra work. He or she said that for upstream area, it is negative. Let me see. So the bigger the upstream area, you have a large upstream area, you have a lot of erosion. Well, I would actually expect a positive beta 4 because the larger the upstream area, the more downwards you are in your catchment. So the thicker the soils would be. But we can think about that a bit more later. Okay, so and then I really like that you're responding and to the chat. So it's very important that you also for your teaching experience, your learning experience, that you engage, that you interact. I'll continue now with the lecture because otherwise we'll get into time trouble. We might get that anyway, so let me hurry up a little bit. So this residual, so the key thing about that is that it can also be spatially correlated. And I'm not going to talk much about that, but just to tell you that in geostatistics, and maybe some of you are familiar with that, we can characterize spatial correlation with what we call a semi-variogram. And a semi-variogram is just some kind of a graph, the red line over here, that plots one value, the semi-variance, against another variable, the distance. So let me explain what this is and this is. But distance is simply the separation distance between two locations on the Earth, two geographic locations. Two locations can be maybe 5 meters separated, 20 meter, 500 meter, 20 kilometer, 1,000 kilometer. It's just a geographic distance between two locations. And the semivariance, I'm not going to give you the mathematical equation, is simply a measure of the difference between, in our case, the soil property at those two locations that are separated with a certain distance. And what we see is typically, as this is an increasing curve line, because at short distances, the differences between the soil properties are less smaller than at large distances. Actually, it's the first law of geography, that everything is related to everything else, but near things are more related than distant things. I hope I cited this first law properly. Anyway, you could Google it, the first law of geography. And that's actually what you find here in the semi-variogram. The larger the distance between two locations, the more variable the soil. If you want to know more about this, well, you have to look into the area of geostatistics. You can become an expert in geostatistics, and then that will be the only thing you do, because it's a really very large topic, and there's a lot of work done in that area, also in soil science. Okay, when you do geostatistics and you make maps, you do spatial interpolation, and you benefit from the fact that observations are spatially correlated. And when you do geostatistical interpolation, then we call this Kriging. So I'm not sure if you ever came across this term. You can Google it, look it up. I can even share with you books about this if you're interested, how to do Kriging. And regression Kriging is one form of Kriging. It's a bit, basically, it combines regression, because here in this slide, we had actually a regression. You remember statistical linear regression, but we also Krig, geostatistically interpolate the residual. So it's a combination of the two, and that's called regression Kriging. So how does this work? I'm not going to explain. We don't have the time for that. Select explanatory variables and you fit your regression model. So you basically do what, maybe you use SPSS or R or all kinds of statistical software to do multiple linear regression. It's a pretty standard. Every statistics class would do that. Then you compute your residuals, and you quantify the spatial correlation of the residuals by computing the semi-variogram. You apply your regression model, because you have a fitted model, you have the beta coefficients, you apply it to each and every location in your study area, usually grid-based. You interpolate the residuals using geostatistics, and you add up the results. And that's what is, in a nutshell, regression Kriging. I'm not sure if you all understand what I'm saying, because I do it really fast. If we had more time, I could go into the details of that. But let me just illustrate it with an example. Okay. Here is an example from another country in Europe, Croatia. Croatia is in the southeast of Europe. It has this kind of a shape over here, and Zagreb, the capital, is somewhere over here. But we're going to look at this square area, a square area which is 50 by 50 kilometers. And here are all our explanatory variables that we use in regression. And here are the locations where we had measurements. If you look very carefully, you can see black, more like dots, I think they are, or asterisks, but there are also pluses. And the pluses were put aside observations. They were used for validation. So they were not used to fit the model, and I'll come back to that in a minute. So we applied regression Kriging. We also applied just regression. We also applied ordinary Kriging. This is a Kriging which does not make use of covariates. And we used the existing conventional soil map as a predictor. And so we had 4 ways of interpolating, of making a map of the soil depth, because I forgot to mention that. But this was an example where, let me see if this, where we did this mapping the soil depth again. Here are those measurements again. So the soil depth in that area varies from 0, bare soil, to 30 centimeter depth. And some parts you have a thick soil, and some parts you have a very thin soil. So here were those 4 maps, and well, we can compare then what you typically get with ordinary kriging. You get a very smooth map. With regression, you see maybe some patterns that are actually patterns in your explanatory variables. And regression kriging is a bit of a combination of these two. We also did the validation based on those independent, those put aside observations. And we found, and we computed a mean error, so which is a measure of the bias of the systematic error in your mapping, and the root mean squared error. I hope you're familiar with this terminology. Really, this is a very important metric, a measure to evaluate how accurate is my map, how close are my predictions to my true observations, the reality. The smaller this is, the better. And also the smaller this is, the closer to 0, the better. And as you can see here, that regression kriging has had the best performance among all 4 methods. And that was at that time was very good news for us, because we had prepared a paper on regression kriging. Another example. We go to Africa now, to Tanzania, this country. And here are all the soil data, and we're doing soil organic carbon mapping. Here are just another view of the data. And this is the map that was made using regression kriging. So we can see some locations where it's yellow and orange, you have a high soil organic carbon, and where it's dark blue up to black, you have a very low soil organic carbon. Just an illustration, but I give you this example because I wanted to add one more thing, that whenever we do digital soil, I think I mentioned it before, when we do digital soil mapping, our goal is not only to make a prediction, but also to quantify the uncertainty. And we can do that using the lower and upper limit of a 90% prediction interval. And that's what I show you in this slide. So you have on the left, you have your lower limit. On the right, you have your upper limit. So basically, every location in Tanzania, we predict the soil organic carbon with this map. This is our best estimate everywhere. But the uncertainty is quantified in this way, because we say here we are 90% certain that the true soil organic carbon is in between the value shown on this map and the value shown on this map. So what do these maps tell us? Well, you see that they're very different, right? These are all the dark blue, black colors almost. And this is much brighter, yellow, orange, maybe a little blue, but not really the dark blue. So they're really far apart, the lower and the upper, because such of a big difference between the colors. And this basically tells us that the map that we had produced is actually very uncertain. There's a large uncertainty. It's not narrow, it's a large uncertainty associated with our map. And we should be honest about that. It's the best we can do. Okay. I need to speed up a little bit, but maybe, Shabir, is it okay if I take up to the full time? So 10 more minutes? I think I need those.
Sure, yeah. Why not?
Okay, thank you. Thank you very much. Well, we are recording anyway, right? So students can also watch it later. Okay, so another example. Well, I hope you recognize this country. This is the Netherlands again. Wageningen is over here. Amsterdam is over here. And this is a map of the pH of the soil. This is the predicted map, so the best we can do. And this is a measure of the uncertainty. But now I'm not showing you the lower and the upper limit, but I'm showing you animations of possible realities. It's just done also doing geostatistics. I'm not going to explain how it is done, but this, this is showed in animation mode, and each of these maps, and I can make as many of them as I like, could be the true pH map. It's like throwing the dice, right? You don't. When I throw a die, I don't know beforehand what will be the outcome. Will it be 1, 2, 3, 4, 5, or 6? I don't know. I'm uncertain about it. So I use some kind of a random number generator here to also create possible realities of the true pH of the soil. But I don't know which one of these one is the true one. So any one of them could be the true pH map. So basically the differences between those maps that I show you here in animation mode, they tell us how uncertain we are. Okay. So all this was about using regression and Kriging, but I mentioned before that you can also use machine learning approaches. And I'm not sure how familiar you are with this. Um, if you're not, and you'd like to learn more, well, I would really recommend this book because this is a very good book that explains it in fairly easy terms. So it's not trying to make things more difficult than they need be. So it's a really nice book explaining how, yeah, an introduction basically to statistical learning or machine learning, whatever you want to call it. And most of these, they are really data-driven techniques, and they're much more flexible than linear regression because they have the model structure can be anything basically. It is very, how to say, flexible, very free choice of your model structure. So it explores all kinds of structures, not only linear model structures. Often they are tree-based, and here's a very simple example of that, just showing the principle behind. For example, a tree base. So suppose we want to map the soil depth again. And we use elevation, vegetation density, and slope as an explanatory variable. And such a tree might say, well, after we calibrated it, they say, okay, is elevation bigger or smaller than 400? Suppose it's bigger than 400 meter. Then you ask yourself, the slope, is it bigger or smaller than 8 degrees? Let's say it's smaller than 8 degrees. Is the elevation then also higher than 700 meter? Well, then I predict soil depth as 50 centimeter. So this is how this tree works. And so this is a regression tree, you might say. And for example, random forest is many of these trees, and they're done in a very complicated way. But I'm not going to talk about that now. But just to give a little bit idea of the principle of how this works. Uh, they are really very flexible techniques, and they're very promising, very useful, but they do require a lot of data. So you cannot do machine learning, statistical learning when you have only, let's say, 50 observations or 100. You need a large data set to get a reliable model. Okay. At ISRIC, when we do the SoilGrids, we actually use machine learning. We use the random forest algorithm. I showed you this before, just a single slide about SoilGrids. So let's go a little bit deeper into that. This is a map of the sand content in gram per kilogram. And we have that for the whole world. So we also have it, for example, for India. And like I said, I think you're somewhere over here. I'm not sure exactly. So let's draw a big circle because I don't know exactly where you are. And so you can read in this map, the darker the color, the more sand in the soil. The lighter the color, the less sand. So maybe here in this delta over here, is this India or is it already Bangladesh? I don't know. Um, I'm not so good at geography, but so we have a delta here. So I guess you have more clay here than sand. So that is also confirmed by SoilGrids. And maybe also here, apparently, we have more clay, higher clay concentration, because at least the sand concentration, the sand content is lower. But there are parts where sand is very high. Also in the region where you are. So and you can zoom in because the resolution of this map is 250 meters. So we could even zoom in here and see at a very fine resolution, pretty fine, 250 meter, this particular soil property. But you can also do the silt content or the clay or the bulk density and so on. And we also have the uncertainty quantified, right? So the uncertainty map is over here. The lighter the color, the lower the uncertainty, the more accurate the map is. So here we have a high certainty, low uncertainty, but when it's dark, we are very uncertain about the sand content. It's all quantified. And you can, did I mention that? Well, basically, I think it was in the previous slide at the beginning of my lecture. So soilgrids.org is the website that you can visit if you want to know more about this, and you can download and you get all the information. Also a bit of the information of how were these maps made. You could also read this paper. It's an open access article, so you can just download it for free. And it explains SoilGrids, um, the 2017 version of SoilGrids. We have now released recently a new version of SoilGrids. So this, and we have a new paper also in review at the moment, but this is the most recent one that was published. So if you're interested in this, feel free to, to Google this paper and you get all the information about how those maps were made. Yeah, I think I showed this slide also already, but in a little bit different way, that different parts of the world, we have different data density. And for example, one of the things at ISRIC we would like to really increase the sampling density in India, because then our maps can become better, of course. And the maps, we share them with everybody. So if you have soil data, you probably not, but if you do, and you're happy to share them with us, we don't become the owner, you stay the owner, then we would really appreciate that. Okay. Uh, one more example before I close my lecture. So bear with me just a little bit longer, maybe 5 more slides. All that I have presented to you so far is about spatial mapping, static spatial mapping. We predict the sand content of the soil, and we're not interested in the change over time of sand content. And probably that's pretty okay because it's a very static soil property, right? Sand uh, content today is not very different from sand content 10 years ago or even 50 years ago. But there are soil properties that do change over time. pH, for example, soil moisture, of course, but also soil organic carbon. So nowadays we're also working on space-time mapping of soil properties. And soil organic carbon is a very important one because of climate change, right? We know that the more carbon we can store in the soil, the less carbon there will be in the atmosphere. So this is a way to combat climate change. And countries are responsible for monitoring the carbon storage in their soils. And I think every 5 years or so, they have to report to the United Nations what is the status of the carbon in your soil. So from that perspective, it's very important that you're able to also model and predict and quantify the soil organic carbon change over time. So that's what we did here in this study. And we used Argentina as a case study. So we mapped the soil organic carbon of Argentina from 1982 to 2017. So it's a 36-year time period. And all the green dots here are locations where we had soil data. And so, of course, this was a collaboration with colleagues from Argentina, from the INTA Institute of the government, and they have their SIS-INTA, their Soil Information System INTA database, and this stored all these observations. And we not only have the geographic location of every soil organic carbon measurement, but we also knew the year in which the soil was sampled. Of course, we need to know when was the soil sample taken, otherwise we cannot do space-time soil organic, space-time soil mapping. And here you see a histogram of the year of soil sampling. So actually they even had data from before 1965, but we were focusing on the period 1982 to 2017. So let's say basically from here to here. Well, we have a fairly uniform distribution. Well, we don't have many data from after 2015. And this is also a period with not too many data. Here we had a lot of data. So you can see the distribution over time of the data. Here is the distribution over depth, sampling depth. So they took samples, most of them in the topsoil, but there are also some in the subsoil up to about 2-meter depth. And there are gaps over here. You see the sampling density in the south of Argentina is much lower than in the, well, the north or the central Argentina. So we use this random forest model to establish a relationship between the explanatory variables and the soil organic carbon. And well, I really did not explain how that works in detail at all, but it works with these regression trees, many of those trees, and somehow the algorithm selects what is important and what is not. Which covariate is informative and which one is not. And in this implementations of random forest in the R software, you can also compute these what they call the importance plots. So here you get the larger the bar, the more important that covariate. So WCL stands for climate. These are all remote sensing images, right? So this is the link with remote sensing again. So climate is important, most important, parent material as well, terrain and vegetation, because you see NDVI popping up here, you see? So of the first quarter, the fourth quarter, so we divided NDVI over seasons within the year. And it was actually dynamic because NDVI changes over time. So this was our, because we do space-time mapping, we also have a dynamic covariate that actually models the change over time of the soil organic carbon. Because if there is a relationship between soil organic carbon and NDVI, and we model that using our random forest model, then any change in NDVI will result in a change of soil organic carbon stock. Now, I'm really running out of time, but you know, if this year the NDVI changes, this may not have an immediate effect on the soil organic carbon. So you get a bit of a delay, a delayed effect. So we used exponential decay functions to allow that the NDVI change this year has an effect on the soil organic carbon stock 5 years from now or 10 years from now, a delayed effect. I think that's very important to include. Okay, and these are the results, so I'm almost done. Here you see a time series of the predicted soil organic carbon stock in Argentina. And you see here the year counting, you see? So we start in 1982 and we end in 2017. And well, you have to look really carefully to see changes. But if you look carefully, you do see something changing here, right? And here as well. And well, in a way, this is expected because the spatial variation of soil organic carbon is really dominant. That's the major source of variation. But there is a bit of temporal variation too. And you see that also over here, because here you see time series of the total or the average carbon stock within regions and also for the entire country, the entire Argentina. So for example, the orange square blocks over here, they show that over the years in Argentina, actually the carbon stock has decreased. You see, the line is going down, which is not a good message for climate change, right? Because we're storing less carbon in the soil than we used to. And this is for 3 example regions. If you want to know more, I think you have like a 2-page text in your reader, in your literature folder. And I have 2 papers that I put in the references there. And one of them is also about the space-time soil organic carbon mapping. It's again an open access article, so you can simply download that if you would be interested in that. Okay, that was it. So I took more time than I was supposed to. I apologize for that. And I'm not sure if I think you're all eager to go for lunch. I'm ready for my breakfast, but you are ready for lunch. But maybe there's still time for a few questions if you feel like it. Should I stop sharing the screen? Anyway, I hand over to Shabir.
Yeah, you can stop sharing your screen. We have a few questions. Can I ask you questions?
Yes, of course.
Yeah. So one other question is it better to use regression kriging or random forest beyond the sampling area?
So you want to do like extrapolation, basically, right?
Yeah.
Yeah. So well, I think when you do kriging, then extrapolation is very risky, right? Because kriging, the geostatistical interpolation, really makes use of the fact that neighboring information, neighboring values are correlated. It makes use of this variogram. So you cannot do really well spatial extrapolation with kriging. But with regression, you might be able to do that because you establish a relationship between your explanatory variable, like for example, slope or NDVI, your dependent variable. But random forest does that too. And then, of course, the question you ask, Shabir, is, okay, which is more reliable? Um, I think because random forest is more flexible, but we really have to test that. I would expect that maybe random forest machine learning is a bit more comfortable with extrapolation in geographic space than regression. We also, I didn't talk about that, but we have to consider the difference between geographic space, what you're referring to, and what they call feature space. So for example, if you want to map the soil organic carbon in Siberia, in Russia, but you have no observations, no soil profiles over there, but you do have a lot of data in Canada, which is actually maybe very similar kind of environment, similar climate, similar vegetation, then maybe the measurements in Canada can help you to predict in Siberia because they are actually very similar in the feature space. That would be the idea. But yeah, your question, we really need to test, I think, how well does extrapolation work if you do linear regression compared. Does that answer your question? Okay.
Okay. And we have one more question. This
I
is
do see.
about the
Oh,
normal
I see
distribution of a
question
soil
and answer
parameter.
now. That's new to me. So it's not in the chat.
Yeah.
So let me see. Oh, no. It's the same basically. Yeah. But I see now something else. So
Yeah.
is it possible to predict soil carbon stock with the application of using Sentinel-2 data? Okay. You are all remote sensing experts, right? So for me, it's difficult to answer this question. I should pass you on to my colleague, Laura Poggio. She is really, or Titia Mulder. So they're both also in Wageningen. They are experts in remote sensing used for soil mapping. So maybe I'll do that. But so Sentinel-2 is, my answer would probably be yes. Any remote sensing imagery potentially is useful as long as there is a relationship, a correlation between the remote sensing signal and the soil property of interest. So if you have like a cloud of, when you make a scatter plot, on the x-axis you put your remote sensing signal, on the y-axis you put your soil property, and if there's no structure, it's just a cloud, a correlation 0, then it will not be useful. But if they are nicely correlated, highly correlated, then you can definitely benefit a lot from that remote sensing signal to help predict the soil, like the soil organic carbon, what you're mentioning here. And I would say, yes, Sentinel-2 should be very useful. And maybe we could even look in the literature if it has been used already. And if not, maybe you could be the first to do that or to do that in your area. So yeah, so my answer is yes, but I also have to add that I don't really know very well all the differences between the various sensors. So maybe it would be better to pass this question on to a colleague who has more knowledge about remote sensing. Maybe Shabir, maybe you have also an idea about.
Yes. We can
Yeah.
predict it by using the Sentinel data too. There's no problem in that. Gerard, we have one more question. This is about the distribution of your soil parameters. Normally, what we see, our soil parameters are not normally distributed. So how does it affect to the variogram relation?
Yeah. Oh, that's a very good question. So there must be someone. Maybe it was you, but it's all related to the assumptions in geostatistics. And you're very right that when we do geostatistics, when we do the Kriging, and of course I didn't pay attention to that, would be go too much in depth, but we basically assume that this residual, this epsilon, has a normal distribution. So if you map soil organic carbon and you include a trend, whether it be a linear regression or a random forest, then maybe the soil organic carbon is not normally distributed, has a skew distribution, but you have to look really at the residuals. How are they distributed? So if the residual also has a skew distribution, you might consider using a transformation, right? I think you're familiar with that. For example, you could take the square root of the soil organic carbon, or you could take the logarithm of the soil organic carbon. And then after you did this transformation, you apply your modeling to the transformed soil property. And you do the variogram, the mapping, the prediction, the Kriging, all in this transformed space. And then when you get your end result, the map, you have to back transform to the original scale. So in geostatistics, if I would talk more about geostatistics, I would definitely mention that you have to check whether the residual has a normal distribution, yes or no. And if not, you might want to look for a transformation. Yeah.
Okay, fine. Then there is one more question. It's about how to counter the problems of high spatial variability, especially in areas where we have rapid land use change in space.
Yeah. Okay, so high variability in space or in time? Because if you say land use change in space,
yes, in space.
Because so basically, because land use change is change over time, and then of course it will affect the soil variability also in time. But so let's look only at spatial variation of soil properties, because you might have, for example, that in a certain area you have many different land uses, and the land uses are not large areas, but they're like a mosaic of small patches. So this is a cause of large spatial variation also at short distances. If the spatial variation, the high spatial variation that you observe, can be explained by your explanatory variables, for example, land use, and if that explanatory variable is able to explain that soil spatial variation very well, and in that way you basically you can you take into account, you cover for, you explain the variation, then you're okay, right? Because basically your map will also have a lot of spatial variation, and the residual maybe not, because all that short distance or that high spatial variation that you observed in the soil property was actually already taken into account by your covariates. But maybe that's, that would be the ideal situation. We often find that in reality, that residual epsilon still has a high spatial variation. Those of you familiar with geostatistics, maybe I think the word nugget did appear in my slide, but I did not explain what it is. But it's really a measure of the short distance spatial variation. And that's a nuisance, right? We don't like it. We don't like that, because it basically means that the soil property at this location over here may be very different from the soil property maybe just a few meters away or 20 meters away. Short distance spatial variation. And if you have a large short distance spatial variation, this means that the map will become very uncertain, because that short distance spatial variation is hard to predict. So I measure here, but it doesn't really tell me much about what happens over here, because there's a lot of short distance spatial variation. So that problem cannot really be solved except by, now I'm going to introduce a new topic of geostatistics, going for change of support. For example, block Kriging. For example, let's say we map soil organic carbon content concentration. When we do the machine learning or the regression or the Kriging, our predictions refer to soil samples that have the same volume as the soil samples that we took in the first place for calibrating our model. But so they're really point predictions, as we call them. And maybe the user, the farmer, the government, I don't know who is interested in our final map, is not interested in the soil property at a point support, but they want to know the average, maybe in a hectare or maybe a square kilometer or in a parcel or a field. So basically that's called change of support. You move from point support to block support, to a larger support. You want to know the average soil organic carbon content of a field, for example, or a hectare area. And that has the advantage that the short distance spatial variation actually is removed, is cancels out, is averaged out. Because you have highs and lows next to each other because of this nugget, this noise, but the average is still pretty easy to estimate. So the nugget will not have an effect on the uncertainty of spatial averages. So that might be an escape. Okay?
Okay. Yeah, thank you. So we have a last question and few more questions, but those are more related to remote sensing persons. So I will share them your email. So if you can rope in some remote sensing expert. So here.
Oh, I will do that definitely. Yeah.
So we have. Yes. Thank you. So we have this last question. It's about what is the minimum number of sampling points that we should use for interpolation?
Yeah, very good question. Yeah, so I think I can answer this question in two ways. So the first one is, of course, it depends on the model that you assume, because depending on every modeling approach has certain requirements in terms of number of observations to be able to estimate the parameters of the model reliably. So the more parameters a model has, the more complex a model is, the more data you need. So that's why I said, for example, the machine learning models like random forest, they are they're really data driven, and they put a high demand on the number of observations. And I'm not going to give you like a number. I mean, I cannot say if you have 500, it's fine, but if you have 499, it's not fine. It's not like that. So, but you have to really, at least hundreds of observations, maybe better thousands, if you want to do machine learning. But you can always do this statistical validation or cross-validation to check how well did you do. If you do Kriging, for example, you have to estimate the semi-variogram. So I can share with you some books which you need at least 100 observations, or 80 maybe, or some people say 60, some people say 200, to be able to estimate a semi-variogram reliably. So you cannot do geostatistics with only 25 observations. So really it depends a little bit on the model that you use to decide how many observations do you need. Now, the second way I can answer your question is, how accurate do you want your map to be? Because there are relationships with sampling density and accuracy of your map. So the higher your sampling density, the more accurate your map. So perhaps, your user, your client, or you yourself, you say, I want my map of the sand content of the soil to have say a prediction interval which is never wider than, say, 8% or whatever. So then you can, if you have a low sampling density, so not too many observations, maybe you don't reach that objective. You cannot satisfy your requirement. So then you need more data to narrow down the uncertainty. So there are actually graphs, especially for Kriging. You can actually, if you know the semi-variogram, okay, that's of course a disadvantage, or how to say, catch-22 or caveat, or so if you know the semi-variogram, you can compute beforehand how accurate your map will be given a certain sampling density, a sample size. I can share with you the paper that some papers about that as well. I don't know who asked this question. So there is a relationship between map accuracy and sampling density. Yeah. Okay. I have plenty of time, but I'm not sure about you. So if you need to stop, we will stop, and I'm happy to answer questions also by email. Yeah. Okay.
Yes.
Shabir.
Thank you for answering the questions. That's regarding about your institute. Are you going to start this summer school this year at the campus, or you will be doing that online?
That's a very good point. So we have, let me share the screen. It won't take more than a minute. Share the screen again. So let me see. At ISRIC, we have every year, we have a spring school. So actually, Shabir, it's not a summer school, it's a spring school. And let me go to the page. You see here the ISRIC Spring School. It's every year in May, 1 week, 5 days. And it has actually, there are 2 courses. One course on world soils and their application and their assessment, WSA. But we also have a course on digital soil mapping, and that's the one that you're referring to. And we will have our course in 2021, and it will be online this year. But unfortunately, it's full. So we have a maximum of 50 participants, and it's full. But this is, I'll put this in the chat. This gives the program, and we'll have it every year. So also next year again. So if you're interested, I think Shabir is interested. So yeah, it would be really nice if you could join.
Yeah, exactly.
And so we
I was trying last year, unfortunately.
I couldn't hear you
last year, but unfortunately because of the COVID, because of this COVID, we couldn't. Manage to go.
That's right.
So
that's right.
Maybe next time I will try.
That would be nice.
It's always wonderful to hear you and seeing you after a long time.
Okay, I think we met in at Enschede at ITC, right?
ITC, exactly. Yeah. So thank you very much for your wonderful presentation, and we hope to see you in our future programs.
Okay, well, you're very welcome, and I once again apologies that I took more time than I actually should have. And I'm happy to answer questions. Feel free to send me emails, and definitely I will answer. And I really hope that we can stay in touch. And if you or your students are more interested in applying digital soil mapping, I'm happy to help out. Okay. Have a nice day. Enjoy your lunch.
So we would like to have collaborations.
Okay.
Yeah, you too. Enjoy your breakfast.
Yeah.
And have a nice day.
Okay. Thank you. Bye-bye. Bye.
Bye-bye.